Hello, welcome back to this video series on program synthesis. Today I'm going to talk about a tricky problem, at least to me it is tricky. The goal is to compute average of two numbers with some properties, okay? The first constraint or property we would like to have is that there is no overflow, okay? When two numbers are added, we know the overflows may happen, right? What we wanted to avoid is overflow of two numbers when they add. And that is the most important one. And the next important one is actually, we don't want to use division, okay? So we need to be able to use other operators like a plus, minus, bitwise and, or, shift left, and so on, but no division, no multiplication, okay? Because these two are expensive. Okay, so how do we approach this problem? It may come across a little bit of a surprise that you wanted to compute average without using division and multiplication. Okay, well, I didn't search online. I'm sure this is a topic for which there are many solutions out there. The solution that I am going to talk about is program synthesis, of course, is let a computer come up with such a program for us, okay? We will tell the computer what we mean by average. We will just give some examples. We will not give a formal specification this time. So what I'm going to do is I'll take this approach, okay? I'll throw in, okay, this is basically an average box that we would like to learn, right? From magic automated reasoning, okay? We will send in two inputs, right? We will say this is my x, or yeah, this is x, and this is my y. And for example, we will send concrete inputs, right? It may be x is 5, okay, and y is 4. What we get out as average is 9 by 2, right? 9 by 2 is 4, okay? So we will train this computer with a bunch of examples like this, and then we will see whether the automated reasoning can come up with the formula that sort of satisfies these two constraints, okay? It must satisfy these two constraints, to be more precise. Okay, so how are we going to approach it? First of all, I have to explain to you why there can be overflow, okay? So I'm going to take a very simple example. Let's say we have a very weird data type which allows us to define 2-bit numbers, okay? So what are the possible 2-bit numbers we can write? Of course, one is 0, 0, and then another is 0, 1, which means number 1, and then 1, 0, right, which is number 2, and then 1, 1. So these are the only possible numbers we can have with 2-bit numbers, right? Assume in this case all the numbers are unsigned type, okay? So what happens if I am asked to compute the average of say 3 and 1, okay? In the real world, you will say 3 plus 1 is 4, 4 by 2 is 2, so average of 3 and 1 is 2, right? That's what you will say, very likely, right? But in the world that we live in computer world, this is not going to be true. Average of 1, 4 will not be 2, not necessarily true. Especially the constraint that I mentioned is that I'm working with only a 2-bit representation, right? So 2-bit representation means you have this clock, almost a clock. I have a 0, right? And I have a 1. I have a 2, and I have a 3. So these are the only possible numbers my clock has. Okay, so what is 3 plus 1? 3 plus 1 means you're at 3 and you take only one step, you end up at 0. So average of 3 plus 1 is actually 0 on this number system. Yeah, okay, this is really weird. Okay, the reason it's weird is that we got into an overflow scenario, right? 1 plus 3 is 0 in our case, because 1 plus 3, if you write it in binary, is nothing but 4. 4 is 1, 0, 0 in binary, and we don't have space to store the leading most significant bit. We just throw it away. That means we are only having 2 zeros, which is nothing but 0. So this is basically the problem now. We don't want to have overflow. So how do we avoid that? Okay, well, I'm going to use the program synthesizer to come up with a program for us, okay? And there will be one more constraint I must have added, actually, is that the third constraint is no if then else statement. No, if then else statement. So no conditional branches, no overflows, no division nor multiplication. So these are the three constraints that I would like the synthesizer to satisfy. And I will train the synthesizer with a bunch of examples like this. Okay. Let's get there first of all. I'm going to show the synthesizer now for you, which is based on the SIGUS syntax that I have been talking in my previous segments. So let's get there now. Okay, so what you're seeing is an empty screen at this point. Okay, so what I wrote is basically unsigned average synthesizer, right? Which is going to compute the average of two unsigned numbers using program synthesis techniques, right? It takes two inputs, X and Y. These are the two inputs, X and Y. And we don't really know exactly how the program will look like. So we are saying you're allowed to use add and or. So all these things you're allowed to use. And of course, since we are working only with 8-bit representation, we will generalize it to 32-bit easily based on the pattern we will see. Of course, when you do this, the shift amount is bounded by 1 through 7, right? Because otherwise the shift left and the shift right are not meaningful. Okay, so here are the bunch of examples that I'm training, right? I'm saying if I am given 3 and 6 in hex, which is 3 plus 6 is 9, 9 by 2 is 4, and same is 6 plus 3, of course. What about 5 plus 2, which is 7 by 2, which is 3? What about 16 plus 16, which is again 16 when you take average? And interesting thing is here now, what is FF? FF is 255. 255 plus 1 is 256. 256 divided by 2 is 128, which is in hex 80. Okay, so here is this beautiful overflow constraint, right? And here is also another overflow constraint. And this is another example. So we give a bunch of examples to the synthesizer. I actually started with only one example before I started the video. I had one example. Of course, one example is totally meaningless. You know, how would it know magically what you're having in mind? Remember, this U average is something that I mentioned here is it's just a syntax. You can call it anything you wanted. So the tool doesn't know what you have in mind. It just takes the syntax. It's trying to come up with an expression sort of match the constraints that you have codified here. Okay. In some of the earlier videos, I used a formal specification, right, to say, come up with this program that match my specification. And now I'm saying, come up with a program that match my test cases. Like basically, if you are from test-driven development perspective, you can imagine you have a bunch of tests and you wanted to satisfy a program. That's basically what you're trying to do. Okay, so with that background, I think I should be able to run this for you and talk about it. Okay, the synthesizer is now trying all possible programs that will match my examples, okay, in a very smart way, using symbolic kind of analysis, SMT solvers, basically SMT solvers. My examples become the guide or oracle for the synthesizer. Okay, so let's wait for a few seconds. It should be out there at any moment. Okay, it's working hard for us. While it's running, I can tell you some of the data about arguments, right? This is my name of the file, and I'm using the syntax guided synthesizer using the CVC4 tool, try to infer the program, which is right away shown now. And let me write it as usual in the regular syntax for you. So we have synthesized an average program, which takes two inputs, X and Y, right? So basically, the program that it is trying to say is this: X comma Y is nothing but what is it? Let's start from the innermost one, right, as usual. So we have to do XOR of X and Y. So XOR of X and Y. This XOR. Oh, I wish I had a better writing here. Okay. So okay. So what you're seeing is XOR of, this is XOR, okay, not to confuse with AND. XOR of Y, and then we do this. We left, this is right shift, logical right shift, right? Logical right shift. Let me call it L to be more clear. Logical right shift by how many positions? Only one position, right? This is one. And then we take this data, we do add. Okay, this is one part of the expression. We add with bitwise AND of this part, right? Okay, so we add with X and bitwise AND, okay, Y, and that's all. This program is nothing but average of two numbers. Okay, we can try now. Let's get back to an example. Let's see whether we can try the example that we started with, right? We started with a scenario of just 2-bit representation, right? And we asked average of 3 and 1. Okay, let's see, when X is 3, what is the bit pattern for 3, which is just 1 1 in 2-bit representation. And when Y is 1, we have 0 and 1. What is XOR of X and Y? If you remember, XOR basically cancel out when the data is same. Okay, so you get this, right? So this is XOR of oh, this is XOR, right? This little symbol in this notation is XOR. Just to be clear, sometimes I use this for AND also. Okay, what about AND? And is very clear, right? X and Y means you're basically checking whether there is any well, first is 1 and the next is 0. This is and then what are we supposed to do? We take X or Y and do a logical shift by one position. That means this 0 will disappear. So we have 1 and a 0. Okay, this is basically the number, right? Right shift by one position, right? Okay, so this part is just nothing but 1. Okay, so now we have 1 and we add it with X and Y is 1. So 1 plus 1 is nothing but 2. Okay, this is perfect. We got 2, which is exactly the average of 3 and 1. So the idea of this expression is pretty neat. It doesn't have if then else statements. It doesn't have division, and it turned out that this kind of tricky ideas are oftentimes available when someone looks into the decompiled version and reverse engineer it from the binary. Some kind of optimization might show something like this. But in any case, the approach that I have shown is the opposite, right? I'm saying to the synthesizer, construct a program which has certain constructs in place that match my examples. So I actually learn a program through examples, right? That's basically what I have shown you. And actually, there is an interesting connection you can make. When you add two numbers, you get a carry, right? Whenever you have 1 and 1, for example, you get a carry. So if you do XOR, you can actually use XOR and bitwise AND to model addition. Actually, that's basically one of the reasons why magically the synthesizer was able to come up with this. Of course, it doesn't know that kind of semantics. It was trying to sort of match up against our syntax. Okay, with examples rather. Okay, so thank you. That's basically what I wanted to show you.